Aliasing. So you have probably heard about anti-aliasing in different games and graphic settings. So now we're going to talk about what is aliasing and where does it come from. In the previous videos we saw this issue that where we downscaled a texture into a 2x2 result and the result was white, although the original texture was mostly black. This issue can be explained by Nyquist-Shannon sampling theorem. So this is a nice sine wave. Now let's sample this sine wave with a frequency of 2.09. So if we keep sampling this sine wave, we get these samples. And now if we connect these samples, we get a different sine wave that has a lower frequency. So our original signal had a larger frequency. And now we have sampled it in a way where the result is a different sine wave, one with a lower frequency. This is called a Moiré alias. The Nyquist-Shannon sampling theorem says that in order to reconstruct a band-limited signal, one has to sample with a sampling rate more than twice the highest frequency. So our period for the original sine wave was 3.14 and we sampled with the sample period of 2.09. If we calculate the frequencies, then 1 divided by pi times 2 would be 0.64. But our sampling frequency was 1 divided by 2.09, which is approximately 0.48. So this is not larger than our required frequency. We would need to sample at least 2 samples for every period. And this does mean increasing the sampling frequency. If we just move these samples to the left, you can see that in this period we don't have 2 samples, we only have 1. Although in the other ones it looks like we have 2. We can also calculate it a bit differently. So if we divide the period of pi with our sampling rate 2.09, then that is 1.5, which is not greater or equal to 2. Now a couple of things about this Nyquist-Shannon sampling theorem. The band-limited signal means that there is a fixed highest frequency in the signal. Now, are the real-life signals band-limited? Well, that's a big question. People have wrote different papers about it, so there's this dilemma: are the real signals really band-limited? In the real world, maybe there is no highest frequency in any signal, but in computer graphics we don't have to worry too much about it, because when we're sampling an image, then the resolution defines the highest frequency we can have on that image. The reconstruction is only possible when we know the shape of the signal. For example, if we sample this sine wave like this and we don't know it's a sine wave, maybe it's this box wave instead. Then if we sample less frequently, we produce an alias. And this is what happened also before. We have our actual signal, the one in black, and we have our samples, and we have sampled an alias, another signal that was not in the original data, but rather was a result of our poor sampling. So the Moiré aliasing comes from sampling less frequently than the Nyquist-Shannon sampling theorem tells us. Alias means generally something unwanted that emerges because of our algorithm, some kind of a signal that is non-existent in the original data, that's masquerading as the original signal. Now if we wouldn't have this black line here, then we would guess that because of our samples and our values here, then that the blue line was the signal that we saw. But in reality there was a higher frequency signal down here, and we didn't get this, we got this alias signal instead. To illustrate this, in SigiLearn there is this interesting example. So this example down here is just a 2-dimensional ever increasing cosine wave. So the cosine wave starts increasing in frequency the higher the coordinates go from 0. So over here we just have this nice white area, so the peak of the cosine wave, and it kind of falls off. Now if we increase our sampling step, we try to fit more and more signal into the result, then we can see that the cosine wave starts increasing in frequency. The change is getting higher and higher and higher. And if we keep increasing this sampling step, trying to fit more and more of this signal into this small resolution that we have here, we can see different weird patterns emerging. Some kind of a repetition or some weird shapes that are really not existing in the data. There is no shape like this in the cosine wave. This only becomes apparent because we're sampling with a too low frequency for this high frequency signal here. Coming back to the Nyquist-Shannon sampling theorem, often it assumes that these samples are taken over time. So this is basically how radio works. And this theorem comes from signal processing. And it's often used in like sampling electronic signals and reconstructing audio from radio waves and so on. Now from this video, you should understand aliasing. So aliasing is when an algorithm creates a pattern that is not existent in the original data. It creates some kind of an alias. And when we look at the result, we see the alias and we don't know like what was the original signal underneath it or original pattern. You should also understand the Nyquist-Shannon sampling theorem, and to avoid this Moiré type aliasing, we have to sample with the rate at least twice the highest frequency of the pattern.